Okay, so this is a live broadcast. For some reason, I can't find the link to it. So I'm gonna search around real quick to try to find the link so that way everybody can come on here. So give me 1 second, I'll be right back. Come on. Where's my link? Here we go. Okay. All right, guys. Sorry for that. I know that was like a whole lot of time in the beginning of this video, of this live stream, to just kind of see me kind of dilly-dally with my computer here. But I had some trouble getting the link out. It just automatically, like, the page just disappeared. So I had to go and reset that link. But I got the link up, so we'll see if we get any viewers in here, and then I will start on going over some stuff with the last two chapters in the Bach, Vellum, and DeVoe book, which was on chi-square tests and linear regression t-test. There were 3 chi-square tests that we covered, and this is just kind of some fill-in while I wait for some more viewers. So those people that are watching this on already played have something to listen to. So we had 3 different chi-square tests. We had a chi-square test for goodness of fit, a chi-square test for homogeneity, and a chi-square test for independence. And that was on chapter 26. Chapter 27 was about linear regression t-test. And in both the linear regression t-test and the chi-square test for independence, we're trying to see if there's an association between the 2 variables. The difference is that in a chi-square test, we have 2 categorical variables, and we're looking if there's an association between those 2 categorical variables, whereas in a linear regression t-test, we're looking for an association between 2 quantitative variables. So we would do those in different ways. The difference in the hypotheses of those 2 tests is in a chi-square test for independence. You know, it's pretty much the same. They are actually pretty much the same thing. In words, you can write them the same thing. So we would have the null hypothesis is either being, as being there is no association between the 2 variables, whatever those 2 variables are. And this goes for chi-squared for independence and for linear regression t-test. And for the alternative hypothesis for linear regression t-test, it would be, and chi-square test for independence would be that there is an association between those 2 variables. The difference, though, is the kind of the idea of why we do what we're doing, like what we're really testing. In a linear regression t-test, we're testing if the slope is 0, or actually the null hypothesis would be if the slope is 0, and then the alternative hypothesis is that the slope of the population is not 0. And the reason for that is because if the slope was 0, right, if we had a 0 slope, then it would say no matter what happens in our x variable, it doesn't matter what happens in our x variable can change. Our y variable is going, our y values are going to stay the same. Okay, so they're going to stay uniform. So if that happens and the slope is 0, then there's going to be no association between the two variables, because really it doesn't matter what happens to x. Y can, what doesn't matter if x changes, y is going to be the same thing all the time. So that would be our null hypothesis, is that the slope was equal to 0. If there were an association, then we would see some sort of slope, either positive or negative. In the linear regression t-test does not tell us what the slope is. If it's negative or positive, we have to do our linear regression and see that information. All it tells us is whether or not there's an association. It actually doesn't even tell us if it's a good association, just that there is one. So we would want to do some more work. So I'm going to go ahead and get started with a couple of problems that we were doing in class today, where we left off. Kind of where we left off, I'm going to quickly go through, remind everybody what we did in the beginning, and then I'm going to do the next problem. So we're looking really at two problems. We're looking at a linear regression t-test and a chi-square test for goodness of fit. So let's take a look at what I got here. I'll show you my worksheet. Okay, I think we're going to go. We're going to go infinite maestas here, I think. Let's see if I can pull this up here. Ah, hadn't set that out already. Okay, all right, there we go. Just like my computer, not to be loading. Ah, here we go. All right. So I'm going to go ahead and screen share this with you guys. So you should all be seeing my iPad here. Okay, so here's the problem. You might need to zoom in a little, zoom in on your screen if you can. I'll zoom in as much as I can here. We have this problem here about student progress, and what we're trying to see if there's an association between the math test score in the comprehensive test of basic skills and the reading test score in the comprehensive test of basic skills. So we've got all this information here. We've got all this information that came out of a computer, and we've got our plots. This is our scatter plot here. This is our residual plot, and this is our histogram of the residuals. So what we did in class is we talked about our hypothesis. So I'm going to go ahead and write these hypotheses. I'm going to zoom in a bit so we can see what they are. And we just talked about it just a second ago, right? Our null hypothesis is that our slope is going to be equal to 0. And our alternative hypothesis is that our slope is going to be not equal to 0. Now remember, you do want to write these in context, just so the people in the AP exam know what you're talking about. So we talked about this. I'm just going to go ahead and say it. I'm not going to write it out because it's going to be too long here. There is no association between math test scores on the CBS, I think it was the CTBS, and reading test scores on the CTBS. Okay, and then the alternative hypothesis is going to be that there is an association between the two variables, in this case, math and reading scores on the CTBS. Why did I keep messing that guys up? CTBS, okay. Are the assumptions of regression satisfied? We talked about this in class. Yes, they are, and you just have to kind of just go over them real quick. All right, we have 4 of them. You just have to make sure that you check all 4 of these. And if you're watching and you're not in my class, because you got this on a after I did it, or you're on live stream, I don't know. We need to make sure that it's straight enough. So you want to go back to here and make sure that the graph is linear, fairly linear, okay? You want to make sure that the residual plot is appropriate so that there's no fanning out. Now, it kind of looks like it fans out, but it really doesn't. To fan out, we would need a couple more dots like right there, so it really looks like it fans out. But this one does not. It's fairly scattered. So since since the residuals are fairly scattered, we can say that the linear regression is, or the linear model is appropriate. So that's another thing you want to check. So that would be, you know, 1, 2. You want to make sure that the data are independent, and of course you can say that using what I just talked about. And then the last one here, you have to make sure that the so I did, there's 3, sorry. Okay, we got 1 is that there's no pattern in the residuals, 3 that they don't fan out, okay, and 4 that the residual plot is fairly unimodal and symmetric, which it is in this case. So you check your assumptions and conditions. So let's see, it says, what do you conclude? So what do you conclude? We got to come up here and take a look at our information. And right here, we're always going to look at the one, okay, let's zoom in here. We're always going to look where it says variable. We're always going to look at the one that does not say constant. Okay, the one that says constant, this coefficient one right here, the one that says constant, this is going to be your y-intercept. But we're not really looking at the y-intercept now. There might be a case where you did, but we're not doing that. We're looking at the slope because we want to see the significance of the slope. So what we're going to look for is always whatever this other variable is in context. And the coefficient of that, this is going to be your slope. The standard error, right there, SE of coefficient, that's the standard error of your slope. And you're going to keep going, and then you have your t-score. And then finally, this last number here under probability is your p-value. And you notice our p-value is very, very small. It's so small that it's less than 0.001. And, you know, we really don't have an alpha level that's ever that small. So that's kind of why we can just leave it at that. So let's go back down to our conclusion here. What do we conclude? Well, I'm going to conclude, conclude, sounds like cuckoo-y. What do you conclude? Well, since our p-value is, I'm going to say, incredibly small. Okay, what's the p-value? It is less than, in fact, it's so small, it's less than 0.0001. Okay, and I got that from here. We reject the null hypothesis. So in context, there is strong evidence that there is an association between reading and math CTBS scores. Is that, again, guys, I forgot. Oh yeah, CTBS scores. I would say I forgot a keyword here, average. Okay. There is an association between the average reading and math CTBS scores. I don't want to forget to use that word because that's kind of that's really what we're doing. We're looking at averages. Create a 95% confidence interval for the true slope. Okay, so the formula for that is going to be B1 plus or minus T star degrees of freedom times the standard error of B1. So I'm gonna plug everything in that formula that I have, and I know B1 was OB1, 0.865. Shrink this down here so I can write this in here. 0.865835 plus or minus. I need my T star with how many degrees of freedom? 18. So I'll keep parentheses here for that. And my SE is 0.1045. So I need to find my T star here with 8 degrees of freedom, or 18 degrees of freedom. For 95% confidence. Now, in order to do that, I'm going to need to go to some sort of T table. And, you know, normally you can find a T table in your in the back of your textbook. So I'm just going to search for one right now. Find one real quick online. I can, but it's very small. Let me share this with y'all. Let me share this with y'all. Okay, so I'm going to stop sharing that. Y'all see me again, and I'm going to share my screen, and you're going to get infinite maestras. Okay, let's go over here. So hopefully you see this. This is my T table, and I am looking at degrees of freedom here. I have 18. Zoom in a little bit. Whoa, that's nice and zoomed in. So 18 degrees of freedom. Zoom out. It's too big. Let me get in here. There we go. Okay. So we have 18 degrees of freedom, and we have a 95% confidence. So let me go. I got to go all the way down here to 95% confidence. Okay, so I'm going to go up 18 degrees of freedom. It looks like I have 2.101. So again, 95% confidence, 18 degrees of freedom, 2.101. Okay, so let's go back 2.101. Let's go back to the iPad here. Put that in there. 2.101. And then we are going to plug that guy in a calculator. Okay, so I think I'm going to use my TI-Nspire because that's what I love to use. Give me a second to bring this up. If you're out there, you can. Well, you're obviously out there because you're watching this. So if you have a TI-Nspire, you should get that bad boy out and start plugging this stuff in there, and get your confidence interval. Now, the problem doesn't say interpret the confidence interval. It just says create the confidence interval. So that's what I'll do, and then I will interpret it in the next part. Okay, so here is my calculator. I'm going to enter that in, 0.865835. We're going to go plus first, 2.101 times 0.1045. And I get 1.08. Okay, that should be my high end. All right, so that's my top end, 1.085. And then my low end is going to be when I subtract. So I'm just going to copy and paste here. Make a subtraction. And I get 0.64. Now, those don't seem like very, it seems like interesting slopes. Well, what's that telling us? That's telling us that we are 95% confident that the reading score will be higher on average, somewhere between 0.646 and 1.086 points for each additional point that's scored on the math part. So that's not exactly what I said in class, but that is the idea. So the idea is, as the X value, which in this case is reading score, as the reading score increases by 1 point, we're going to expect to see, on average, an increase of about blank, the slope, for the other score, for the other variable. So in this case, since we're talking about 95% confidence interval, we're saying for every increase in reading score, we're going to see, on average, 95% confident that on average, the increase in math score is going to be somewhere between 0.646 points and 1.086 points. So that was a little bit different in class. I said that the average rate of change is going to be between, which is perfectly fine to say that, because that's really what the slope is an average rate of change. But in context, I wanted you to kind of understand, kind of go back to what we talked about before, a long time ago when we first went over linear regression, that the slope is, as we increase for one increment of the X value, we're going to expect on average an increase or decrease, if it's negative, increase or decrease of so-and-so, whatever the slope is, of the Y value. So now that we're dealing with a confidence interval, all we're going to say is, we're going to say the same thing, but we're going to say we expect that the math score increase by between, right? The math score is going to increase on average between this amount and this amount. In this case, 0.646 and 0.86. Okay, so that would be the the interpretation of the slope for the 95% confidence interval. Now, if you want, I'm going to put it on the screen really quick what I have in terms of that answer. Okay, so let me do that one for you. Okay, so here you go. I know it's kind of hard to see, but we're on E right here. I know it might be difficult to see there. We are 95% confident that the reading CTBS score will be higher on average between 0.646 and 1.086 points for each additional CTBS point scored on the math CTBS test. So what I'm going to go and tell you guys here is, if you don't have enough time to copy this down, because I'm going to switch right now to the next problem, just go ahead and, after I'm done here, just go back to this point. I don't know exactly what point we're at, but go back to this point, pause it, and write it down. Okay, so I want to have enough time to go through all the problems. So let's go. I'm going to go back up here to our last problem. Car colors. Okay. So go ahead and read that to yourself if you haven't done that. Okay, so hopefully it looks like my volume's working, because somebody said that they're not getting any volume. So if you're not getting any volume, put it in the comments so I know. I don't know how long ago that was. I might have just been rambling on for the last 20 minutes with no sound, but it says that I have sound, so let's hope so. Okay, so let's go through this last one. According to Ward's communication, 90% of sports car enthusiasts prefer a red car. How fitting, we had a car show today at school. 16.2% silver, 14.7% black, 14.1% green, 14% white, 22% other. And then, so that's what we expect, right? We expect those to happen. A sample of 250 cars in a NASCAR raceway revealed 45 red cars, 42 silver cars, 34 black cars, 40 green cars, 39 white cars, and 50 other color cars. Are NASCAR color preferences typical of sports enthusiasts? Test an appropriate hypothesis and state your conclusion. So we can see right away this is going to be a goodness of fit test. And we know it's going to be a chi-square goodness of fit because we're trying to match to see if any of what we expect to occur matches with what we already have. All right. So we have to do here, excuse me, we have to write our little table here. Of expected values and observed values. Okay. So let's start off with our hypothesis. So I'm going to zoom in just a little bit as we go on, so you can see what I'm doing. Okay, my null hypothesis is that NASCAR color preferences are typical of sports enthusiasts. Now I know you're saying, but wait a minute, Mr. Miasis, that's what we're trying to. That's kind of what we're trying to show. Well, because that's what it says in the problem. But when we're dealing with the goodness of fit, our null hypothesis is always that it fits. Okay, our null hypothesis is always that our expected match up with, or that our observed match up with our expected. That is our null hypothesis. What we're trying to see is if they don't match up. Okay, so really, our alternative hypothesis, regardless of what it's asking for here, our alternative hypothesis is that NASCAR color preferences are not typical of sports enthusiasts. Again, it really has to do with the null and alternative being, you know, the null for goodness of fit is always going to be that they do fit, that they are the same, that they are typical, and that the alternative hypothesis is always that they are not. Okay, so then now let's look at our assumptions and conditions. Okay, our first assumption is that we have counted data, right? Okay, so our, oops, can't even spell our. Our data are counts. That's pretty much all we have to say. We're going to show a table that's going to show these counts in just a second, but that's kind of all we have to say once we, all right. The second is that, okay, so we have counted data, we have random, duh, right? Random. Okay. We're going to say that a sample of 250 NASCAR. Well, we're just going to say that assume that the 250 cars were taken at random. Okay, and our third one is going to be our expected cell frequency. And we need to show that those are greater than 5, but I'm going to go ahead and write that down. The expected cell frequency is greater than 5. So now we're going to show that. We can't just let that hang there. We have to show that that's true. So we're going to make a little table here of our observed and expected. All right, so we're going to take our observed numbers. We have, let me title these guys up here. We have red, silver, black, green, white, and other. I'm going to need a total of that too. We're going to write those in here though. Let's do some black here. All right, so we have 45 red, 42 silver, 34 and 40, 39 and 50. And we're going to need a total. Because we need to make sure that the totals add up, right? All right, so let's do a little calculator work. Now, what we're going to need to do is, there are 19% of sports that prefer red. Okay, I'm just going to mark this right here in green. Okay, we got 19% here, 16.2% here, 14.7% there, 14.1%. Well, I cannot write that one. Very good. There, 14% white, and 22% other. Okay, so now we're gonna get to some math here. So we'll see if I can screen share a couple things here. Okay. Okay, so I'm back. All right. Here we go. Infinite maestas. Here we go again. Okay, so I've got my notes here. Move them to the side. Oops. I got my Inspire here. This guy, shrink this guy. All right, let's do a little bit of math. So we need to add 45 plus 42 plus 34 plus 40 plus 39 plus 50. We get 650. Okay, so that's our total. Now this one has to also add to 650. But what I'm going to do is I want to know what my expected value is. I'm going to put this in a different color right here. And my expected value is going to be 19% of my total, which was 650. So I'm going to do 650 times 0.19, which will give me 1,000. I gotta make this a little wider here, guys, because I'm not getting the whole thing here. 1,263. So 126. We'll just round up 1,264. Okay. All right. Then we need 16.2%. So I'm going to do. Oh, that's not right. It took too many zeros. Sorry, I got to redo that. 650 times 0.19. I don't know why I was writing that. Duh, right? And have 19% of something be in the thousands if it's 650. Dummy. Okay, so 124. That sounds more like it. Okay, now we're going to do 650 times 16.2%, which is 1.162. I get 105, so I'm just going to put 105. Okay, then 650 times 0.147 gives me 90, so 96. 650 times 0.141 gives me 92. I'm guessing 650 times 0.14 is going to give me the same. Oh, it's going to be 91. All right, so what I'm going to do here is I'm going to take 650 and subtract it from the sum of all of the other things that I have there. 105, 96, 72, 1, and I'll make it 142. That should be that goes in here. Just to double check, 650 times 0.22 is 143, but you know, we can't have that extra 1 in there. We've got to have them even amounts, so 142 will be sufficient. And I know if Leah is watching this, she's going, oh my gosh, Mr. Myassis, how can you just round things like that? But that's the way it works in statistics. Okay, so now that we've got those numbers, we can clearly see that the expected cell frequencies are going to be greater than 5. So now we're going to go to our mechanics, which is really just getting the calculator to do a lot of the work for us. So we're going to go to Menu, Statistics, Stat Tests. And you know what I'm going to do before this? I'm going to make this bigger here. Okay, here we go. And the stat test that we want is, why is it going? Oop, that's confidence intervals. There we go. Stat test. We want a chi-square goodness of fit. All right. Oh, look what I forgot to do. I forgot to enter in my list. So listen, spreadsheets. My first one's going to be OBS for observed. In fact, if you want to, you can just get all crazy and put observed. And this one you could put expected. All right, so let's go ahead and fill those in. Okay, my observed were 45, 42, 34, 40, 39, 50. My expecteds are 124, 105. Guys, these look pretty off to me. I don't know about you, but they look off to me. I don't know if I added this correctly. Something doesn't seem right to me. I feel like I did something wrong. Let's go back here. Look at, there it is. Put a 4. Dang it. Well, that messes me up. It's a good thing I caught that, right? Jeez. All right, so it's 45. 250. Oh, man. How disappointing is that? I'm gonna go. I'm gonna go look at my comments. Thank you. You put 445 when it's supposed to be, and that was a while ago. Rookie mistake. Yeah, thanks. All right. So now I gotta fix that. Oops. All right, 250. Man, I guess it's just getting late for me, guys. All right, let me crank these out real quick. 250, 0.19, 47.5. Your expected values don't have to be whole numbers, by the way, guys. I just find it easier to deal with them as whole numbers. because remember that expected values are really like means, so they can be decimals, but I just find them easier to work with because I'm putting things in the calc when I'm getting this last bit, this last number right here, 55. Let me make sure they add up. Plus 48. I want to make sure that everything adds up correctly. See too much. So 54 is what I'm going to use. So let's do this over again. Okay, go back here. The good news is that I don't have to do too much work after that when I come back over here. 48. Thank goodness I am not using an 84. If I was using an 84 right now, I would be pulling my hair out. Okay, so now they got my everything corrected. I'm going to go ahead and go up here and go ahead and do my menu, statistics, stat test, chi-square goodness of fit. My observed list is, look at that, observed. My expected list is expected. My degrees of freedom, 1, 2, 3, 4, 5, 6 minus 1 is 5. And sure, I'll do that. Look, you can also shade the p-value, so it'll show you a picture, but I don't know if your calculators do that. That just might be mine. Okay, hit OK. Let's see what we got. We got our chi-squared, so you're going to want to write your chi-squared value down. You want to write your p-value down. You want to write your degrees of freedom. And you don't need pretty much anything else. Those are what you need. So look at those p-value. Look at that p-value, 0.8597. 0.8597. So what we're going to do with that p-value is we are going to say 0.8957. We're going to say that, okay, so we write down, so our mechanics here. We got a chi-squared value of 1.92286 with 5 degrees of freedom and a p-value is going to be 0.859713. Okay, so that's a pretty big p-value. Let's go ahead and take us home. Take me home tonight. All right, here we go. Conclusion. With such a large p-value, and we got to state the p-value, 0.859713. We fail to reject the null hypothesis. There is no evidence to suggest that NASCAR preferences are, I'm going to use a big word here, different word, are atypical. Okay, atypical means not typical, right? Of sports enthusiasts. Again, we're failing to reject the null hypothesis, thus saying that there is no evidence that this happens. Okay? No evidence that the alternative hypothesis will occur. Okay, so I did kind of 2 problems, a long-winded, and because it was a mistake. Sorry about that. Excuse me, I need to go get some water here soon. So I'm going to go ahead and open it up for a few questions. You can use the comments to make questions. I'm going to run and go get some water real quick. You're a dingus, huh? Very nice. All right, any questions before I leave? I don't know how long that digging a deeper hole was. So here's the thing, I see your comments now. And I don't know how many of you are still on. I'm gonna end this off pretty soon here, but I don't get a chance to look over the comments very quick while I'm going. I'm just going. So that's the hard part of a live stream, is that, you know, I can't see all those comments as I'm going. Anyway, I'll give you, another 30 seconds. I am looking at the comments right now. If there's no comments, then I am gonna go and hang out in my living room, watch some TV. Watch the Warriors play right now, which I don't know if they're winning or losing. They were losing when I left, so we'll see in just a second. Okay. You're using the wrong numbers. Not too bad. Man, I just kept making it worse and worse, right? All right, guys. I think that's it. Good luck tomorrow. Study. All right. That's all I gotta say. Study this test. I think you'll be fine. All right. Okay, guys. I will talk to you soon. I'll see you tomorrow.